This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, let's start. So welcome back. Does anyone not have the handout for now? Yeah, okay. So come grab. Okay. So what we are doing now, we are continuing the angular momentum topic. We are kind of jumping angular momentum, inertia tensor, angular momentum, inertia tensor for the time being. What we did was angular momentum about which point? G, which is the center of mass of a rigid body. Okay, this is what we did so far. Angular momentum H about point G, okay, center of mass, and inertia tensor about point, the same point, all right? What we are doing today is, well, sorry. So we did this, okay? Now we are going to do H, angular momentum, about, I'll call this point O. O will be, in this lecture, the center of rotation for purely rotational motion, which I will define what that means. Okay, so we will have a special case. And also about some general point, so I'll call it C. C would be some general point. Okay, so O is center of rotation for purely rotational motion. Okay, I'll also do this purely rotational motion in short, and C, some general point. So we need to discuss these two things in this hour. All right, so the first thing I'm doing, just because normally the lectures are spread through the week, this will be just a reminder about angular momentum about the center of mass, the first thing we did by definition, okay, just a reminder. And then I'll define what is purely rotational motion, what this thing means, okay, and then we'll discuss this thing, and then we'll discuss this thing, and maybe between them there would be some examples, all right, some examples. All right. So this is the revision of this, H about center of mass. Formulas to remember. The definition, instead of the triple integral, we brought it to this form. If we could find in advance what is I. Sorry. Tell me when I don't have the pointer. I forgot to set it up. So this first one is from the definition of angular momentum about center of mass, all right? What is this? So, okay, this is some, this is not relative angular velocity. This is important. This is the absolute angular velocity of the rigid body of which you are finding angular momentum. Okay? In this case, it is expressed in frame G, because when we were doing these derivations, we made some assumption that frame G, this frame G, is attached to the rigid body, and so the frame G and the body, they share the same angular velocity. Okay, so remember, this is absolute angular velocity. I repeat, absolute. Students have the tendency to look at a relative angular velocity. Okay, remember that. Don't use relative angular velocity, absolute angular velocity. Okay? Now here what you can do, because this is a 3×1 vector, you can rotate this vector from one frame to another by using rotation metrics per normal. And this is the, well, the left-hand side here is what? Golden formula applied on which vector? On h, the angular momentum about g, okay, to get h dot, okay? And if you remember h dot about g, we showed how it is equal for a given rigid body, how it is equal to the sum of external moments applied on that rigid body, where all the moments are summed about point G, the center of mass. Now this formula, the two sides, h dot about G equals sum of moments about G, you can't just arbitrarily use that about any other points, not G, but we will show how it also works for this O, for this special case of purely rotational motion. Okay, so there would be, I'm going towards a special case where something similar could be applied. Okay, not always, just when you have this purely rotational motion. So what is purely rotational motion? I will pause here for a few seconds just for you to read it, and then I will explain it separately. All right. Now, one big trouble I have with this definition is that students like to use their own definition, which is wrong. So don't do that, okay? Stick with my definition. I only have one definition of purely rotational motion. Don't change it, okay? Don't just go, but this is also rotational. No. All right? Just my definition. So you need to think and check two things, like two criteria. One is to find a fixed point. Fixed point, I repeat, fixed point. Point that does not have any linear velocity, yeah, with respect to the stationary space. Okay, so a fixed point. In this case, just to define things, I will call this point O. So think of O as a fixed point. All right? This is the first condition. You can't find a fixed point about which this purely rotational motion happens, then it's not purely rotational. All right? Then the other thing is, let's say this is the rigid body. All right? Its motion has to be such that, yeah, I'll just kind of freeze it. Let's say this is the rigid body. Okay? So any point, any arbitrary point on the rigid body, and you should be able to pick any arbitrary point, the vector going from this O to P, ROP, it can change direction, but it must remain with the same magnitude, same size. Okay? So the distance between this point O, which is fixed, I remind you, to any point of your choice on the rigid body must remain constant. The distance remains constant. Okay, so I'll give you some examples of what is and what is not purely rotational. So let's say if this is the rigid body, if it orbits this point O like this, so can you see how its orientation is changing? Its orientation is changing so that every point remains with the same distance to point O as this moves, okay? So this would be purely rotational motion about this point O, which is then the center of rotation, all right? Now, if this body is doing this, so you can't see well, but I can also take it not just in the plane, but also outside of the plane, okay? It can do like a spherical orbiting about this point O, okay? As long as I keep all the distances between this rigid body to point O the same throughout the motion, it's purely rotational. Now, if it does something like that, yeah, can you see I'm not changing the orientation now? Now distances change, right? Because, say, this is the distance to, say, this point here. And now, as I'm rotating it to here, the other side, it's further away. Okay, so the distance changed. Okay, so this is not purely rotational. Okay, even though O is fixed and we are going around it. All right. Now, if say O let's say you have let's say this is the cap, okay, and this is point O, and here you have a pin, okay, and this thing can rotate, so O is not fixed, okay, even though the cap could only orbit this kind of point O, okay, orbit around it, because it's not a fixed point, then this cap is not doing purely rotational motion, all right? Now, what about if the cap would do this? Is it purely rotational motion? Sorry? Yeah. So it is purely rotational motion, just not about O. About the point about which it rotates. Yeah. So it could be G or any other point. All right? Any questions about what is purely rotational motion now? So remember, you are looking for two conditions: constant distance of any arbitrary point. Yeah, I mean all points on the rigid body, their distance to point O, and that point O has to be fixed. All right? Don't alter the definition. Okay. Now, just to strengthen it, I want to. So this is like a little comics thing, okay? Just to make things faster, I'll just let you read. Ask me anything if it's not clear. So, in this lecture, I'm assuming that this rock is a rigid body performing purely rotational motion about this point O, which is fixed. Okay. P would be this point over which we are integrating, yeah, going around. So now O is fixed, yeah. This vector, ROP, this is important, and I will explain later. So the direction can change, but the magnitude is constant. Yeah, does it make sense? Now here is a coordinate system that I located for convenience here at point O, but what you need to remember is that it is attached to the rigid body. What does it mean? So let's say this is some xb, yb. So this frame B moves together with the rigid body, okay? Its orientation changes together with the rigid body. Can you see my hands? Yeah, okay, so like this, okay? Now, saying that the origin is O is just like what I said before with frame G being located at the center of mass. It's pretty arbitrary, just for you to later remember that as you take projections of vectors going from O to P, they start from O. Okay, you will take their projections onto the axis of this blue frame B. Okay. Okay, next. Now, this vector, ROP, for any chosen point P, this vector appears constant. It's not really constant because it changes its orientation, but it doesn't change its orientation relatively to this frame B as the rigid body orbits around point O. So all the so for a given choice of point P, its components along the xb, yb, zb will remain constants. Yeah, constants throughout the motion. This is important to understand. Yeah. I will repeat that because I'm sure some are sitting quietly, not understanding what I just said. So let's say this is t equals 1, and at t equals 2, I have this rigid body moving a bit to here. Okay, now this will be point P. Yeah. Same point on the rigid body, and this is the vector ROP. So the vector itself is not a fixed vector, it's not stationary, but this frame also moved, right? Because it is attached to the rigid body, right? So this is at 1, and this, let's say, is at t equal 2. Okay, so this would be xb at time 2 and yb at time 2. Okay, this has rotated. This angle are the same. Okay, so the distance is the same, and now as I will be drawing the projections of this vector ROP onto the axis of xb, yb, I will have the same projections, right? Same projections. So the vector ROP, when it is expressed in some frame B which is attached to this rigid body while it performs purely rotational motion, these will be, I think I'm calling them RXB, RYB, RZB. They will be constants. These three will be constants throughout this purely rotational motion. Okay, is it clear? Now we will be using the fact that these are constants, yeah, as I'm varying time. This is not, it is not to say that this R dot is 0, right? But within this frame, it appears constant, so we will be using that fact, okay? We cannot use that fact if it's not purely rotational motion. Why? Because we won't be able to attach such a coordinate system that moves together with the rigid body. Okay? And and the ROP vector remains having the same magnitude. Okay, so it's all combined now. Any questions? I hope you are on the same page with me. So this slide doesn't have too much meaning, but essentially several things. You will see that now we will be able to calculate angular momentum about this point O or about point G. And we will need to make choices. Okay, I'll come back to it. Everything we are doing now is a special case of purely rotational motion. It will not apply to general motion, which is essentially not necessarily purely rotational motion. And then this frame B, again, we will be able to choose infinitely many such frames that are attached to the rigid body. Okay, so I'm not concerned about a particular orientation. I just need to choose one orientation of frame that is moving together with the rigid body and keep working with it. All right, so now what we are starting to do, having understood all of these definitions, we are starting to calculate the angular momentum of the rigid body about this point O, which is the center of rotation. It's called center of rotation. Okay, so just for this special case of assuming the body performs purely rotational motion. Okay, so this is what we are starting to do now. Okay, and we will also relate H dot, just like we did here, H dot equals sum of moments about G. We will relate H dot about O to the sum of moments about point O, okay, which might be beneficial down the road, okay. And the actual derivation is very similar in terms of the algebra. It's very, very similar in terms of the algebra, but it's not the same at all in terms of the assumptions, the underlying assumptions. Because here we use the property of the center of mass to make some terms 0. And here we will use this property of center of rotation, essentially, to make some other terms go to 0. And what we have here is, by definition, I want you to recognize the different terms again. So this thing, rho dV, is the mass of a little cube of volume, right? Infinitesimal cube of volume. Rho dV is its mass. Mass times its absolute linear velocity, ROP dot. So all of this thing is the linear momentum of an infinitesimal point P, yeah, with little mass rho dV inside the rigid body. Okay, so it has its so point P. Now point O could sometimes also be on the rigid body. Okay, it doesn't matter. Point O is fixed. Okay, so if point P is some arbitrary point in the rigid body, some kind of volume, all right. So think about the linear momentum, and then if I want to calculate the angular momentum of this little piece of volume about this point, I will need to do the cross product between this vector and the linear momentum vector. Okay, so the linear momentum would be ROP dot, which is the absolute linear velocity. It has to be absolute for linear momentum, has to be absolute, times the mass. Yeah, so rho dV, that's the linear momentum of this piece of volume, and this is vector ROP position, and when I cross them, it gives me the angular momentum about point O of this piece of volume. Then if I sum all of these pieces of volume throughout the rigid body, I get the total angular momentum of the rigid body about point O. Okay, so sum all of them with this dV infinitesimally small, this will be the total. Okay, so this is by definition. Fine? How does it, what is different from what we did before? What we did before when there was G. In here, what was different? Right, it was RGP, okay, but this didn't change. This didn't change. It still had to be the absolute linear velocity, okay, for linear momentum. So RGP, now it's ROP, okay? Okay, so what we are doing now that we already fixed this blue frame, which I remind you moves together with the rigid body, in order to make to go from this integral definition, in order to go to some kind of I omega more convenient definition, we will do some steps to do this cross product kind of once. Okay, so I would need to define ROP and also calculate ROP dot using the golden formula. All right, so I'm defining here this omega b. What is this omega b? It is the angular velocity, I would say absolute again, absolute angular velocity of frame B, but also the rigid body, because they move together. They share the same angular velocity. Okay, so absolute angular velocity of the rigid body and the blue frame as well, all right, expressed in frame B. And these Rxb, Ryb, Rzb are the coordinates of this vector going from O to some arbitrary point P. Yeah? This vector, maybe I'll put it, it's black here. Black. Yeah. So this is ROP. Sorry for the mess. Okay, now this is changed with respect to time, but when you freeze time, or when you, not freeze time, when you think about just the area, sorry, the volume, you vary point P along this volume. Okay, so you don't need to think about anything moving. Okay, so remember these are constants. All right. Okay, so what I want to do now is to substitute back as we did before. If you recall the angular momentum about G lecture, it will be pretty much the same. So we are going to get the same expressions, just the meaning of this Rxb, Ryb, Rzb is different, because now we take this vector from point O rather than from point G. Okay, this is essentially the difference. Okay, and now why is this all zeros? Because according to the golden formula, we need to take the term by term derivative, and since these are all constants in frame B, because it is attached to the rigid body, since they are constants, taking these derivatives of constants would give you zeros. Okay? Okay, so this is why it's written here that we have used the assumption of purely rotational motion. We wouldn't be able to have them as constants if, say, the distance in frame B, the distance would change. Okay? This is one assumption. All right. And another assumption is that here, point O, it's the same O as this one. Okay? And in both cases, it's a valid fixed point. Okay? If it weren't a fixed point, we couldn't, if O was not a fixed point, we couldn't use here O. okay, by definition. Okay, so when you substitute to the golden formula and then you substitute all of these values back, do the cross product, do the algebra neatly, you come to the conclusion that it looks the same, like I omega, like before, where I is just like before, okay, the same stuff, but these R xb, R yb, R zb go from point O to point P instead of from point G to point P. Okay, so very similar algebraically, but totally different assumptions. Okay, so essentially all the integrals you can just do, but you will have different limits. Okay. All right. So this is just the summary. This would be the inertia tensor. This I with the O on the right left, sorry, right top right, is the inertia tensor of the rigid body about point O, which is the center of rotation according to our assumption. Okay. No questions? Right. So this is a very important slide to just summarize the kind of 2 lectures, this one and 2 lectures ago. Okay. H and H, angular momentum, once about G and once about O. Okay. Now this one about G is equal to I omega, and this one equal to I omega. Both of these omegas are absolute angular velocities of the rigid body. Okay? Both of them. It's just that G and B could possibly have different orientation, one with respect to the other. These I matrices are different. Okay? They have different values inside them. Okay? But this definition works in the special case of purely rotational motion. Okay? This is good for a special case. This is good always. All right? So you will, when I say this is good always, a lot of minds are shutting down. Okay, I will always use only this and I'll forget about that. Don't do that. Why? I'm not teaching you that just because I love to give you special cases. It is very useful. Okay, it will save you work later. Okay, in those special cases, it's very useful. All right. Is it possible that frame G and frame B are essentially the same frame? Yes, it's possible that they are co-oriented by choice, if this is your choice. Okay, so you could have, say, this frame G passing through, say, the center of mass, and just doing the same thing as this frame B. Okay, could be or not. Okay, depends on your needs. Any questions? No questions? So this is for H related to I omega instead of the integral definition for the case of purely rotational motion. Okay, so this is about point O. And now we are doing the relationship between H dot and sum of moments when H is calculated about O. And again, I'm working here under a very strict assumption of purely rotational motion. Okay, so a rigid body performing purely rotational motion, otherwise it doesn't work. So I'm back to the definition, the integral definition. This is for H itself, the angular momentum. Now, from here to here, I'm taking time derivative, okay? A time derivative in the more pure sense, not the golden formula sense. Okay, so this is H dot, but so this is just one derivation you are looking at, but later on you will do H dot from H using the golden formula. Okay, once you have a problem, a specific case of a rigid body performing some motion, you can calculate h and then h dot using the golden formula. Okay, this is just to prove why this is true. Okay, so in order to take the time derivative, I'm treating this as a product, so it's a derivative of a product. So this becomes r dot in here and unchanged here, and this r dot becomes, so it's unchanged here, and here it becomes r double dot. All right? And now let's look at these terms. So this one here survives as is, right? And this one here disappears. Why does it disappear? Because r dot OP and r dot OP, yeah, this is a scalar, but both of these things are the same. So they are parallel, and their cross product gives you 0 vector. All right, so is it clear why this disappears? And remember, this is good because your point O is a fixed point, okay, which is an important assumption under the purely rotational motion envelope. All right? Again, if you had G here, like some lectures ago, then RGP dot cross ROP dot wouldn't go to 0 because of the same reason. It's a different reason. Okay? I hope you understand. Okay? Point O is fixed, therefore it serves for both the linear momentum of point P and this vector ROP, okay, to make it angular momentum here. All right, so now from here to here, I'm replacing the mass times acceleration with the force, okay, and then overall it's the sum of moments about point O, right, because I'm taking my force arm, or how you call it, moment arm, yeah, moment arm from point O. From point O to point P, cross with the forces applied on point P. Okay, so I'm calculating overall the sum of external moments. Remember how I mentioned that the internal ones go canceling each other? So I'm left with the sum of moments about point O. Okay? Now this gives you a very similar result to what we had about G. Okay, so again, comparing the two lectures, it looks pretty much the same. This is applicable always, all right, always. If you are working about the center of mass, you can always work like that. And this one is applicable only in the special case of your rigid body performing purely rotational motion, okay? Strictly according to my definition of purely rotational motion. All right. And you will see that this one will be mostly more straightforward to write down in details. I will explain why a bit later. All right, so now we are looking at some examples, and after these examples, we'll go to this one about the general point. All right. So maybe I'll keep it here. Okay, so any questions so far? Did you understand this slide? This is applicable always, and this is only for rigid bodies performing purely rotational motion. Okay? And what is the difference essentially? For this one, you will be summing moments about point O. Here you're summing moments about point G. And in order to get H dot, you can use the golden formula, right, in the respective frame. And H dot comes from H. And H, in this one, it will be I omega where I is about point G, and here it will be I omega where I is about point O. Okay, so you will need to look at that. Okay, so what is this equation here? I'm looking at link 1, okay, and I need to decide, first of all, whether link 1 performs purely rotational motion or not, and if yes, about which point. So as long as I assume that point A is fixed, if A is a fixed point, which it is in this problem, then link 1 indeed performs purely rotational motion about point A in this case. Why? First, A is a fixed point, and second, all the distances between A and any other arbitrary point of your choice along the rigid body, this distance will remain constant throughout the motion. All right, so because because this link 1 complies with the purely rotational motion assumption, I can use the angular Newton-Euler equation either kind of about the center of rotation, which is A, which is this first option, or I can go to the always applicable case to work about point G. Okay? Now, the left-hand side is the application of the golden formula on H. Okay, so the left-hand side is H dot. Here it's H dot about point A. Here it's H dot about point G1. Following? Right. So H dot equals sum of moments in both of these cases is fine, right? Now, why am I working in frame 1 in both of these cases? Why? Because of this I. I mean, I can represent omega easily in any frame, right? And I can also sum moments in any frame. You will see later. But this I can work with I in a different frame. But frame 1 is conveniently attached to this rigid body. Okay, conveniently attached. So it will be easy for me to calculate the inertia tensor of this rigid body in a body fixed frame, yeah, where so the axes of this frame are kind of parallel or normal to the link. Okay, if you go to calculate I, if you would choose to use, say, frame 2 to calculate I for link 1, you will have some cosines and sines of this angle beta when you come to define these vectors. Sorry, this vector, the components here, they will not be constants. They will not be constants, so it won't work easily, all right? We want them, if you want them constants inside the definition of I, I'll go back here. Yeah, so these, all of these are RXB, yeah, and the same for RXG, RYG, RZG, yeah, all of these. If you want them to be not depending on this angle beta, you would rather work in the body fixed frame, okay, which in this case is frame 1. Okay, if you come to calculate it. In general, like very, very generally, you can work in any frame. Okay, I'll show you more details later. Now for link number 2, this one, you don't have two options. You have just one option. Why? Because it does not perform purely rotational motion. And so the only option we have is to use this general formula. Okay, this is always applicable about G, the one we learned 2 lectures ago. Okay? And this is the other example. Look at OC here. If you want to calculate, not to calculate, to write down the Newton-Euler, the angular Newton-Euler equation for this link, this rigid body, link OC, does OC perform purely rotational motion? So it does this, yeah? Point O remains fixed throughout the motion, right? Point O is fixed. Even though this rotates, the point itself doesn't go anywhere. And all the distances to point O, yeah, from anywhere on this wing, all the distances to point O would remain constant throughout the motion. Okay, so even though it's a three-dimensional motion, still it is purely rotational. So for this link, I am still capable of using either of these two formulas, all right? The first one is H dot equals sum of moments about point G2, the center of mass, and this one is the Newton-Euler, the angular Newton-Euler about point O. Okay, any questions? Now, I'll come back to the idea of why, this is the comment here, why use the second one? Like, why not just use the first one always and forget about the second one? So I want you to think about the right-hand side. If I need to sum the moments about the center of mass, okay, about the center of mass, the gravity force itself, assuming it kind of points downwards from the center of mass, won't have any effect, right? Because I'm summing moments about the center of mass. But I will need to take into account all the kind of reactive forces here at the joint O. And these are unknowns. So I would need to take them into account in here. Okay? And because they are unknowns, we would need to get rid of them at some point, and it will be troublesome. Still possible, definitely, but troublesome. And here, if you are summing moments about O, you will need to use the force, the gravity force, okay, but it is a known force. It's a kind of mg, known force, all right? But you will not need to take into account all of those unknown reaction forces at the joint. And it will save you calculations, all right? So this is useful. Are you with me? Cool. Let me know if you don't fully understand. And now this one here is this third case. Okay, now it's not as nice as before, but still it is important for you to know sometimes it will be perhaps convenient for you, or if you know this one, you will be able to explain the other ones, okay? Or, I don't know, maybe I should give you some proof in the exam, I don't know. Okay, so this is H about point C. Point C here is a random point in space. It could be, it could be in motion, essentially. It could have velocity, all right? So H about point C, look how here I still assume that point O is a fixed point because I defined this part as the linear momentum of some point P on the rigid body. Okay, so this is the linear momentum. It has to be with respect to some fixed point O, right? And this is the vector going from C to P. Okay, so it becomes, by definition, the angular momentum about point C, okay, of a piece of volume, and then I'm summing all of them using this integral. So in order to go from this integral definition to something more useful or familiar, I would need to split this CP vector to CG plus GP. You don't have to, of course, but it's just some property. It's a very useful property. I'm sure some of you used it in physics when you were doing angular momentum exercises. It kind of boils down. You can look here. This RCG, I put it outside of the integral. Why? it doesn't depend on point P. All right, so it can come out. And what's left here, if there was no dot, it would be just the definition of center of mass relative to point O. Okay, so this is the derivative of it, so it's just like the r dot of the center of mass. Okay? Times m, m. And then this one here is the definition of the angular momentum about point G. Okay? At this point, I always feel like you are letting go. Don't let go. Just ground yourself back. RGP from the center of mass, okay, to the arbitrary point P, and this is the linear momentum of point P. So together, the angular momentum of point P relative to the center of mass. Okay, so this is h about point G. All right. So h about some arbitrary point C is like h about the center of mass, so kind of how much the body rotates about its center of mass. And then this thing, which is like treating the center of mass as if it were a particle concentrated, O in point G, having mass m as the total mass of the rigid body, okay, and calculating this angular momentum of the rigid body, of this particle concentrated at G about point C. Okay, is this familiar? Does it look familiar? It was familiar before you fell asleep. So wake up. This is, say, the rigid body, point G, some point C. Okay, so let's say you have this as hg, angular momentum of the rigid body about point G. Okay, and to this one, you would need to add, in order to get h about point C, you are summing this with this. So angular momentum of a kind of particle-like mass of, so the total mass here, yeah. So m r, if this is point O, some fixed point, yeah, ROG dot, this is the linear momentum, and you cross it with this vector from C to G. Okay? So treating, so kind of doing as if this is the relative angular momentum, okay, of the rigid body relative to C. All right, let's take a break. This is the last slide here. I think this is the last slide. So I'll be back in 10 minutes, all right? Let's take a break. So what we were doing most of the time, we were talking about h and h about g and h about o, okay? And in both of these cases, there was the new player inertia tensor, either about g or about o. So the idea is that you can calculate, you can kind of transition between them instead of recalculating from scratch. If you know one of them, and for this purpose you don't even need O to be a fixed point. If you know the inertia tensor about G, you can find the inertia tensor about some other point. Okay? The only thing that we would need is to find, so if this is the rigid body, this is G, and this is some other point, which I will call point O, okay? And if I need to, I just need to stick to the same colors. So if we have a coordinate system here, yeah, and the same orientation coordinate system here, so it is essentially the same coordinate system, okay? So what you will be able to do, if you have I about G, you can find I about O, and vice versa, in the same frame, okay? So I just called this one G and this one B, okay? But it is the same. So either, so let me put it F and F, okay? Same. Okay, as long as it is pointing in the same direction, so co-oriented. Okay, so this is what we are going to do as a shortcut calculation, because if you are given this one and you need this one, you don't want to start calculating integrals from scratch, right? You want to utilize it. So what you will need to work with is this vector going from one point to the other. Yeah, and you have this slide here that I was distributing. So this is essentially the theorem that we are going to work with, okay? Now what I will do, so this is the presentation of the theorem, right? I'll just show it to you, explain it to you. We'll prove it. The proof is pretty trivial, and then I'll show the example, which is less trivial, but a very good example, all right? So keep this one for in order to follow me throughout the example. Okay. So what do we have here? This vector, ROG, yeah, this is the vector, ROG, and its components, right? Its components, if I would present them either along the blue or the red frame, they will be the same because it's the same orientation, right? So if I define ROG in either of these, yeah, either, maybe I'll put here B or G, because we assume that they are kind of parallel. I'll put this parallel sign, which means XB and XG are parallel, YB and YG and are parallel, ZB and ZG are parallel, right? So this, I define it as delta X, delta Y, delta Z, distances along these axes between these 2 points. Okay, is it clear why these are the same? I project this vector, ROG, I project it onto the axis. It doesn't matter these ones or these ones, they have the same orientation. So the projections will be the same. Okay? So is it clear what delta x, delta y, delta z are? Now if accidentally you go from G to O, you will have minus, 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 right? But in this formula, which you will easily remember once you remember the other formula here, right? Same logic. So you can remember this one. They come in couples, delta x, delta y, delta, yeah, or something squared, and therefore, if you do the vector from G to O, okay, it will be the same result eventually. So it doesn't matter if you go from O to G or G to O. Okay, but record these delta x, delta y, delta z, and this is the relationship between the inertia tensors about O and about G. Okay, again, B and G as frames, they are co-oriented. This is the underlying assumption here. They are co-oriented, and so when you are working with a given rigid body, let's say you have this frame. So for some rigid body, let's say this frame is convenient for you to work with, yeah. And if this is the center of mass, G, yeah, and this is some other point of interest, O. So if this is, say, XF, YF, ZF, you can calculate IG in frame F, yeah, of this body, and then use this formula to calculate I in the same F about point O. Okay, because you are using essentially the same axis, and you will need to express this vector ROG in that same frame F. Okay, so this is what this formula is useful for. Okay, so this is plus the mass of the rigid body times this matrix, which, just in short, because I don't have a good name for it, I'll call it distances matrix or distance matrix. Okay, so you place all of these components of this vector ROG in F. You define it as some delta x, delta y, delta z, and spread them according to this formula here. All right? So just what to do, can you understand? Yeah? Will you be able to calculate the inertia tensor about some point, given the inertia tensor about the center of mass? Yeah, using the same frame to transition. If you are given this vector, or if you can calculate this vector ROG in that frame, right? No questions? I'm sure you're familiar with this, at least with one axis. Okay, but this is the 3D form. Okay, so what we're going to do now is to quickly prove it. Are you with me? Yes? So to prove it, I'm going to start with a what I'm going to do is just so have a look at this one. I'm going to just give two examples, one with this and one with this, okay, and then the rest are quite the same, okay. So for this one, yeah, this is the definition. about G, yeah? And what I'm going to do is substitute instead of Ry and Rz, oh, not really. I'm going to kind of, sorry, not this one. The similar one for point O, yeah, so this one, ROP, I'm splitting it to ROG plus RGP. RGP has the vectors with these components. Yeah, I'll let you have a look at it. And, oh, sorry, my pointer is missing. So our ROG is this vector that we found, yeah. Our GP is the vector with these components, yeah, Rx, Ry, Rz. Okay, and the similar thing would be with Rxb, Ryb, Rzb, with the components of the vector ROP. ROP from this point O to the arbitrary point on the rigid body. Okay? So if I would break down ROP as the sum of these two vectors, yeah, this is what you get here. Okay? Make sense? And what I'm going to do now is to substitute Rxv, Ryb, Rzb into these integrals. So instead of starting from Ig, I will start from I about point O. Yeah. So this one, yeah, it has these components, and if I look here in particular, this would be I x b x b, right? And just like this one, but YB ZB, right? So triple integral r rho r x, sorry, r y b squared plus r z b squared dv. Okay, and instead of this and this, I'm going to substitute. So instead of the ryb, substituting delta y plus ryg, delta y plus ryg, and here delta z plus rzg. Okay, substituting. All right, and then I just need to open brackets and see what happens. Now this is a reminder. I will use that. This I'll come back to it shortly. So this is the substitution. All right. Opening brackets and just rearranging. So let's discuss these terms that we are getting. So this delta y, delta z, they are constants in, well, if you think of these as body attached frame F, then these are constants. Okay, because they are constants, I can take them out of the integral because just point P is moving, okay, as I integrate throughout the volume. Okay, so I can take them out, and what I'm left is rho dv here for these two terms. So for this rho dv, the integral over the volume is just the mass itself, right? So that's why I'm having here this m times delta y squared plus delta z squared, which is this part here, okay? This times m. And now I need to show you the rest. So these two, they become 0. I'll explain why. So because let's look at this one, for instance. 2 delta y are yg. So because delta y is a constant as p moves, right? I can take it out together with the 2 out of the integration, and then it becomes integral over ryg rho dv. Okay, so yg, if you remember, ryg begins where? At point G, the center of mass, right? Begins at the center of mass, going along the yg direction until it gets to point P. And this multiplied by rho dv is like, remember the property of the center of mass. So for that property, this is what we said. If we spread all the arrows starting from the center of mass, we get the 0 vector. We are kind of averaging, finding where is the center by standing on the center already. Okay, so we kind of come back to the 0. All right? So this is the property. Remember this property? I told you to remember. Anyone doesn't? Does it ring a bell? Yes? No? Yes for this row? Okay. Yes, okay. If not, return to the lecture about the linear momentum and center of mass, and you'll find it. And what I'm doing here, this RGP is a vector. It has 3 components, but this is the 0 vector. Okay, so I can just explicitly split this RGP into its 3 components, the x, the y, the z components. And these are these rxg, ryg, rzg. Okay, so these 3 are the scalar equations corresponding to this vector equation. Okay, and therefore, if you look at just this middle one, this is 0. That's why this term will go away. Okay, and now, so similarly, this term will go away as well, right? And these two, if I look at the triple integral of this, it's just the I xg, right? These two terms. My sister asks if I can talk. All right, so this is ixg, and I replace it here like this. Okay, so you can look. This is the example for the first component. Okay, so remember, this is a big matrix. This is a big matrix. Okay, I just did the first component. The second example for this one is very similar. This is for xy. Yes. So for the xy, I again substituted, instead of rxb, delta x plus rxg. So kind of the x component of the split here. All right. And similarly here, all right, open brackets, this thing comes out like that. These two things become what? 0, right? According to the property of center of mass. And this one here corresponds to the definition of I x g y g. Okay, here. Okay, without I do it without the minus, so that's why when I substitute back all of this thing, it is with the minus here. Okay, you can have a look later. It will make sense. All right. So I will skip the rest, right? And this is the proof. Do you get the proof overall? All right. Done, proven. And now we are going to the more important thing, which is how to use it. So we are going to the example. So for this example, the task is to calculate. So find I, inertia tensor of the swing, about point O. Okay, I will soon tell you in which frame, but essentially we will be working with a frame that is attached to the swing. Now, what you have here, this thing is, this is not part of the swing, this gray thing. You can even assume that it's fixed. Okay, and let's say you have two parts here. This part, this one, that goes from O until the bottom of the swing. Okay, let's say this is a metallic part. Okay, and the rest, which is in red here, the rest, let's say this is a wooden part. Okay, so they have different row. So, but all of this from here, this thing here, O is one rigid body. Okay, not the gray part. Okay, so the swing is the rod, okay, the metallic rod, let's say, and the wooden seat. And the seat has a hole in the middle so that the metallic rod would be inserted until the bottom. All right? So how does it move? How does this swing move? It doesn't just move back and front. So it has this back and front motion, but on top of that, it can rotate about this rod. Okay, have you ever tried some swing like that? Okay, no, good, because it's annoying. Let's say this is, where am I? It looks too similar. Okay, so if this is the swing, yeah, it goes like this, and it can also rotate like that. Okay, or if it's my hand, then kind of like this. Okay, and that requires 2 degrees of freedom here at the joint O. I will be talking about degrees of freedom later, but this kind of 2 degrees of freedom joint, we will call it universal joint. Okay, you can Google universal joint and look at how it can be constructed. Okay, so it allows 2 degrees of rotation. All right. So what are the frames here? This is frame 0. Frame 0 is a fixed frame. Fixed in space, it doesn't move. Okay. Then frame 1 is an auxiliary frame. I'll move here. So frame 1 kind of moves back and front about this y0 or y1 axis with angle theta 1. So it only describes this motion. Okay, it is not attached to the swing. Why? Because the swing can also rotate about the metallic axis as well. Okay, so frame 1 is an auxiliary frame, and then to attach a frame to the swing, I'm using another frame, frame 2. Frame 2 should rotate about this Z1. Okay, so this Z2 will be shared, will be the same. Okay, so now do you understand this picture? This is just the forward-backward motion. Okay, about y1, this is like the main swinging, and now the yaw motion about the metallic axis is here with angle theta 2. So what I want you to understand is that frame 2 is the frame that is rigidly attached to the swing. Okay, this is the body fixed frame attached to the swing. Okay, so what I want to do is to calculate it all in frame 2. Okay, again, I'll stress frame 2. I added it here. If you have old slides, I just updated it today. Frame 2 is the one attached to the swing. And then when theta 1 and theta 2 are 0, frames 0, 1, and 2 will have the same orientation. So essentially, when theta 1 and theta 2 are not 0 any longer, the swing would still look like that always in frame 2. Okay, so in frame 2, x2 will always kind of go front of the swing, z2 will always go towards the metallic rod, and y2 will always go like from hip to hip. Okay. This is a major problem I had last year, so I changed the slides a bit. And then I will be showing frame 2 here as the frame attached to the swing, okay? But I didn't have time to make the changes in the little pictures, so the little pictures are still looking like that, okay? But remember, all the calculations we are actually making are with respect to this frame 2, which is going to be like either of these frames. So this F here is going to be for us frame 2, okay? This and this are all for us, in this example, frame 2, okay? They are, so frame 2 is attached to the swing. Okay, does it make sense? Okay. So how to find it? How to find it? What we are doing is using everything we know so far. Superposition. So we are going to split the swing into 4 parts. I will discuss it soon. For each of these parts, we are going to calculate the inertia tensor about the center of mass of that part, and then use the parallel axis theorem to move from the center of mass of that part to point O, and then point O being a common point, we are going to add all of these parts. Okay. Okay, so again, we are splitting the swing into 4 parts. For each of the parts, I'm calculating first the inertia tensor about the center of mass of that part, and then using the parallel axis theorem to move to point O, and then I'll have these 4 parts, their inertia tensor is about point O, right? And then I can sum them, because they will all be about the same point in the same frame. Okay, and now let me know why should I do about point O? What is my overall interest later on? Right, some moments about point O, because then I don't need to care about any reactions at this universal joint. And can I use the Newton-Euler equation about point O, the angular equation about point O? Yes. Why? Because the swing performs purely rotational motion. The swing performs purely rotational motion about which point? O. Why? First, O is a fixed point. Okay? And second, all the distances to point O remain the same as this swing does this motion. Okay? So as you are getting a headache, still you are not, any point like your eye doesn't go further away from point O. Okay? All right? So what are the 4 parts? The 4 parts are, I forgot the order. Okay, so the first one is the seat, the horizontal part of the seat, which is one of the forms we already, or one of the geometries we discussed. What kind of geometry is it? So it's a cuboid, but I will be looking at the seat like part 1, the full cuboid. Yeah, so part 1 would be this cuboid, which is the seat without the hole. Okay, the hole will be our last part. And the second part would be the backrest. Okay, so this is, say, part 1, part 2, part 3 will be the metallic rod, all of it, yeah, from point O to the bottom of the seat. And part 4 would have the negative mass to account for the hole. Okay, so just a little hole inside this seat. Okay, so negative mass, but which mass, which density? Of this one, right? Okay, so for this cuboid, yeah, the yellow part here, the yellow is the focus of attention right now. Here, the center of mass, yeah, it's easy to know where that center of mass is. So what you would, well, in order to use this, yeah, you would first calculate this for a cuboid, as we did in the morning, okay? And then you need to find this vector for the distance kind of vector from the center of mass, or from point O to the center of mass of this part, okay? And use these delta x, delta y, delta z components to populate this matrix, all right? So first, this is the inertia tensor about the center of mass of this part 1. Okay, and so this is G1. G1 would be the center of mass of the seat here. All right. And you can compare it to the formula for the cuboid just with the right dimensions. Okay, so this is about the center of mass. Still not shifted. I'm preparing my calculation, all right? Okay, and I will also, what I got so far, maybe I'll summarize it. So I got I part 1, okay, 1 for the rigid body I'm talking about point G1, yeah, so this is G1 in the center, right? In frame 2. Okay, and similarly, let's say G2 is the center here, and G3 is the center here, and G4 is the center here. So I'm going to get I2 and I3 and I4 about their respective centers of mass, okay, all in the same frame 2, which is attached to the swing, okay, or to each of these parts. Okay, so for the backrest, this is it, another cuboid, all right. At home, follow the dimensions in this example. you want me to pause for you to look at the dimensions? So say for the backrest, check. We have H, T, and this one is W. So H, T, and W should be the stars in here. H, T, and W. And look at, so X2, Y2, and Z2 would be the same as these ones in the 0. Yeah, because it will look all the time with this orientation relative to frame 2. Okay, so you will have here coming out X2, here Y2, and here Z2. Okay, so for this one, here this one is W, this one is H, and this one is T. All right, so now check for cuboid. Yes? All right, so next part is this rod, which is what? Geometrically, what shape? We discussed already. It's a cylinder, right? I don't require you to remember by heart, but we just did it today. Okay, so for this cylinder, look at the lecture from the morning, and you will see that this is just the substitution of the specific dimensions we have. Okay, and it happens that the z-axis is just like we did in the lecture. Okay, z-axis is aligned with the cylinder. Okay, and lastly, this little part here, okay, which is the hole, and therefore I will take it with a negative mass. Okay, so minus rho 1. Rho 1 being, so this one has a rho 1. And this is minus rho 1. All right? Okay. This one is a little cylinder as well, right? But its height is just T, the width of the seat, right? Sorry? Oh, good? Okay, so now what I need to do is sum all of them about O, so I would need to calculate for this one, let's say, I would need to calculate R from O to G1, or from G1 to O, doesn't matter. I would need to calculate it in frame 2, okay, and for this one, ROG2 in frame 2, ROG3 in frame 2, and ROG4 in frame 2. I would need to calculate them. Each of them will give me the delta x, delta y, delta z that I need to move from I about G of the part to I about O. So after calculating this, I would find I of part 1 about point O, okay, by using the parallel axis theorem. Okay, just this one. Okay, so I'll do it for each of the parts. I'll apply it for each of the parts and so on. So just let's see for one of the parts, let's say this one, the first part, what is this ROG? I need to go how? From O to G1. How much do I need to go along the axis of frame 2? So along X2 and Y2, I don't need to go anything, just go down along Z2. And this is by how much? All right? So this R minus half seat. Okay? And so this will be my delta x, my delta y, and this will be my delta z when I come to substitute into this formula. Okay? Are you with me? Delta x, delta y, delta z. And so they are here. So I just need I just had the non-zero delta z. So it's here and here. And because delta x and delta y are 0, so all of these become 0. Okay? So this times the mass of part 1 plus the inertia tensor that we already calculated for part 1, so the cuboid thing about the center of mass of part 1. We are adding them, and we should get the overall inertia tensor, of part 1 about 0.0. Okay? Similarly, I'm calculating here the distance vector for part 2. Okay, maybe have a look. Here you have delta x and delta z. Okay, because you are going down and backwards. Okay, backwards is the negative z. All right. And so with these ones, your distance matrix would look like this. Okay. Everything with the delta y would become 0. Okay, and so this is your inertia tensor of the backrest about 0.0 in frame 2. Okay, and similarly, this is for the cylinder, the distance vector, and similarly, this is for this little hole. Okay, the same thing. And here I'm using M4 as the negative rho 1 times the volume of this hole. Okay, volume of the hole, okay, times negative rho 1. Okay, this would be my mass here. Okay, and now after all that, just go back here. Whoops. And sum all of these guys here. Okay, so in assignment 2, you will need to do something really, really similar. Okay, I think assignment 2 should be posted already. All right. Any questions? No questions. Okay, do assignment 2. Thank you very much.
Assignment 1 says to put your answers to 2 decimal places.
Yeah.
Is that like we have to do every answer to 2 decimal places? So we need to like this.
It is programmed to identify an error within 0.01. So
if I put something in with like straight from that like with like 4 decimal places,
you'll be fine. Your answer is correct. You'll be fine.
In this slide, the firm of I, O, V, go to this one,
They are the same. It's essentially the same, same direction.
so we can use this also G.
Yeah.
Anything that's parallel to it.
Yes, that's the idea of parallel.
Thank you.
Sorry. Naim?
Thank you.
Yeah, this ROG like delta Z, like for the particular.
Backwards. Yes, so I need to go from point O to the center of the backrest. From point O to the center of the backrest, I need to go down, right? But how much? Maybe
the hole, when we're considering the density, shouldn't that be the density of the rod?
No, because I did take the entire rod, but the hole is like cutting away from this part. So the rod I did take until the end.
It's not until the end, but this is also rotating with respect to the rod, right? So then shouldn't the rod be inside the hole? It is, but
Yeah, the rod is penetrating until the bottom of the thing.
but the hole belongs to the wood. That's why we're taking the density of it.
Yes, yes.
Thank you.
Just have a question about next time.
I need to go. Sorry.
Yeah.
Be patient next
Yeah,
time.
thank you.
Sorry. Unfortunately not. You haven't seen what I've been doing during the break. I went to feed my daughter. Yeah, she's here. She just doesn't like the bottle, so I'm really, really constrained.
I'll see you next time.
Yes. Or send your question on the forum.
Okay.
Sorry guys, I'm really in a hurry.